the language of the universe.
But I don't understand it.
Hello everybody, welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 61, where today we are back with a history of physics episode. Whoop, whoop. So this was quite requested from us. It was actually Einstein was heavily requested on a history of physics episode. And so today we're going to be talking about Einstein and Bohr and Niels Bohr himself. So, yeah.
Yeah, this is the third episode of the history of physics. The first one we did Newton and Richard Feynman. Yeah. And then after that we did Fourier versus Taylor. And then now we're doing Einstein, Bohr, which is cool because they kind of went head to head in the quantum discussion.
Exactly. I was just gonna say,
talk about, of course.
I was just gonna say, people actually were requesting Einstein and Turing, and a lot of people liked that comment. I was wondering, and to be honest, we were going to do Turing, but then as we were just thinking about the structure, we were just thinking they have really not that much in common. They're in kind of different sectors and stuff like that for anyone who might be familiar with Alan Turing. So, they don't have that much. So I just thought, and we just thought that, Bohr and Einstein would be quite a phenomenal comparison. Or not comparison, just discussion about both of them and their impact in the scientific community. Yeah.
And of course, Einstein has done wonders for the physics community. But a lot of people idolize Einstein, and a lot of people who aren't in the science community itself, they're like, oh, Einstein is this crazy scientist. But there are tons of scientists that are, intelligent in different ways. Einstein was very, in his head, thought experiments, thinking about things that you can't really just set up an experiment on the go and do, special relativity, for example, which I'm sure you're going to talk about later. And, all that good stuff.
A lot of his ideas, as you were mentioning, a lot of his ideas are, so not hypothetical, theoretical, and, in his head that, really can't be reproduced in real life, because that's also the essence of the thought experiment. And, a lot of his...
But they have been tested, though, which is...
Yeah, now with our technology, but obviously at that time...
the time it was tested as well.
Was it this? I mean, at the time, for some of his experiments, like the thought experiment about weighing that light box, for example, I'm just giving those kind of thought experiments. You can't ever really do that to, that level of precision with the instruments that we have. But the thought still exists, so that's what's important.
Yeah, but for example, for general relativity, they tested it during an eclipse.
Yeah, I was gonna talk about that. Yeah, so that's a little more macroscopic changes for sure. Yeah, those we can test.
Before we
what about
actually get into the episode here, so we are now up to 8,300 followers on Spotify, so that's great. Other than that, I think we're at 100,000 or 118,000 downloads now. So thank you so much to everybody that's been downloading our podcast, listening to our podcast. And actually, while you were talking, Ray, I did pick a comment of the week because I realized that we hadn't picked one before starting the episode. But
dope. Yeah, because I was just I just looked for one too.
Worry not. So yeah. If you do want to have your comment shouted out here, make sure to leave a comment in the YouTube comment section, because we pick the comment of the week under last week's episode. So make sure to do that if you want to say something nice, a little, constructive criticism. Anyways, this week's comment comes from Divisible by Zero, who was also there during the live stream. So thank you so much.
I was looking
to everybody
at the same
who actually
comment.
joined the
live stream.
I was looking at the
same comment.
Yeah. We actually did our Q&A yesterday, which we live streamed live of course, on Instagram. We tried to do YouTube. That kind of failed, but anyways. So the comment is, all right, the ending of the video was the biggest mic drop with an explanation of Fourier transformations. Yeah. Whoever explained it to you did a great job. Actually, nobody explained that to me. I kind of like made that whole thing. Well, I of course I read it. I learned it from somewhere, but nobody like explained it to me. Anyways, that wasn't part of the comment. So if you made it make sense, okay. As always, much love. Enjoy listening to you guys at work. P.S. First comment. Ooh, nice.
Ooh, nice stuff.
Very nice. So yeah, thanks for the comment. What do we just start? Do you have anything to say?
Let's get into it. Let's get into the beginning of these geniuses. Let's just say, I think, to be honest,
genii.
I
don't know.
There's no way. No, but to be honest though, like, I don't like using. I think that word is kind of overrated, you know, because like it can really be thrown around a lot. But I think it's definitely applicable here. Like, these two men revolutionized our idea of physics, and especially as like we're gonna get into, like, Bohr was, you know, focusing on a lot on quantum theory. He broke a lot of that, and Einstein himself, you know, had a significant impact throughout physics, and it's gonna always be that way. You know, these guys have made these significant discoveries that, you know, will last because they've been proven. So let's start with Einstein. He was famously born.
Wait, hold on, Ray. Pause here.
Okay.
My mic is recording significantly less on one side.
Okay. Quick pause. No worries. No worries.
Oh, it's back now. Okay.
It's back.
Go
It's
ahead.
back. All good? Okay. So Einstein, famously born on Pi Day, March 14th in 1879. And that's basically all I know about his birth. He was quite a child. I believe his parents actually thought he was going to turn out slow because he had a lot of language problems. He couldn't talk, and, like, you know, a lot of his, you know, skills were, you know, a much younger mentally aged person than they were when he was older. So, you know, they were just a little worried. Little did they know. But so he continued to, I believe when he was 16 years old, he gave his first entrance exam to the famous Polytechnic University in Zurich. That is now known as ETH. I'm not going to try and pronounce that, but it's called ETH. And he actually failed his very first examination. Interestingly, a lot of people think, and I know this is a myth with a lot of people, that Einstein was bad at math. I think that just
true.
I think that just to make people feel better about them being bad at math. But no, Einstein was quite phenomenal at math and physics. However, he failed the examination simply because of his language skills. So he actually, I believe, like, he topped the math and physics section of the examination, but he basically miserably failed in the language section. So he couldn't pass the whole thing. So he failed out of that. But I believe a few years later, he then got admission in the same university. No, wait, which university did he get admitted to? That's a little sad here, but yeah. So he was in Zurich, and then he went to a whole. There was a whole military situation with him, I believe, and yeah, he moved to a teaching post. But where did he go to school after that? Did he continue at Zurich?
I believe it was the same.
I think it was, because I believe he taught there as well. Because I remember, like, going to Switzerland and seeing the school where he taught at, and I believe it was in here. So it's probably one of these universities. And anyway, so obviously now we know him as a very successful scientist, and we're gonna get into his contributions. But that's just, you know, a little bit about his early education and just like him as a child. Let's hear a little bit about Niels Bohr.
Yeah, so for Niels Bohr, he was born in Copenhagen and in Denmark, and actually on the 7th of October, 1885. Now, what year did you say Einstein was born in?
Einstein was born in 1879.
1879, yeah. So they were relatively close to each other, right? So, like we're going to talk about this later, of course, when we get into their actual work and all that stuff. But like the discoveries that were being made while they were alive, they were kind of at the same level, right? Like either in university, graduated university, postdoctorate, all that stuff. And so you can see, like, as discoveries were being made elsewhere, those things influenced their works and so on. So you can kind of see that come into play later on. So anyways, at 18, he started his undergraduate in physics at the University of Copenhagen. And it was never a doubt that he was going to go into physics. He, of course, you find an interest. We could probably, figure out the classic question, if we end up, I don't know if there's like a deep fake type deal.
Imagine.
Actually, a little bit of an aside, about GPT-3, the AI who like knows like who has like conversational skills and all that stuff. Anyways, it's I'm pretty sure I read about the fact that it can like impersonate anybody. And so someone did it with Einstein. So he was asking him questions and it was answering as if like the AI was Einstein and giving like answers based on Einstein's work and Einstein's life, and it actually could answer questions about physics and all that stuff. Anyways, I would be kind of,
but yeah, it would have to do a lot of work behind the person that it's obviously trying to emulate.
Well, it's like Google, you type in the answer and it answers, but it's different, it's like a, I forget the name, like it's like Siri, but it's just
so you can't like ask it. So you can't like ask it original question. Oh, you can.
You can.
Oh wow.
Yeah. Anyways.
Oh wow. Okay.
So yeah,
that's pretty impressive.
I was gonna say, he's actually Niels Bohr, of course. He was born into this pretty rich family. His dad was a physician, and his dad actually had a laboratory that Niels Bohr would do experiments later on in his career. So at the end of his undergraduate experience, he actually wrote a paper, or more like an essay, on surface tension. And we're not actually going to go into that very deeply, but he ended up submitting it quite last minute, and he won. It was quite a phenomenal paper. And then later on, he added to it and published it. And so after that, he got his doctorate degree, or PhD, in 1911, and his like final dissertation was on the electron theory of metals. So that's awesome. What about Einstein?
Wow. So I did a lot more history on his actual scientific papers than him, unfortunately, because because I guess point of this episode as well is to kind of talk about how they have reshaped our thinking of science, a lot of them especially. So I think the most notorious thing, especially when we're talking about with Einstein, maybe we can get into it, is the year 1905. Now, the year 1905 for Albert Einstein was also known as Annus Mirabilis. Now, I might not be pronouncing that correctly, but it translates to Year of Miracles. Now, you might be wondering, well, what is so miraculous about this year and Albert Einstein, right? In this one year, Albert Einstein changed science, basically. Now, most people, it takes them quite some time. But, obviously, I'm not saying that he didn't take a long time to work up to these papers. But in this one year, Albert Einstein released 3 extraordinary papers that would then go on to revolutionize science. So we can start with the very first one. So in March of 1905, Einstein releases the quantum theory of light. Now, this is quite revolutionary. Now remember, Max Planck, I keep messing up because it's a German. Max Planck was very famously known about deriving his emission spectrum and radiation spectrum for objects that basically for for black bodies, and the Planck spectrum, for example, is very well used in black body radiation. And understanding when I say black body, I mean any body that has some temperature above absolute zero will emit radiation based on the Planck spectrum. So Planck was huge in that regard, right? Now Einstein comes up and he's like, well, let's try and see if we can apply this to light as well. If we can try and break up light, because remember, at this time, light was thought of simply to be a wave, right? It was kind of known that all electrons, or not known, but it was thought that, again, atoms and electrons weren't really a thing. So any subatomic particles were... Sorry?
That's not perfectly accurate.
What's up?
You said that at the time, light was thought of as a
As a wave.
But that's not true, actually. Like,
wave particle duality was in
further,
1920. In 1923, that was later.
Even further back, like in the 1700s, Newton actually thought that light was a particle. And then also people like Christian Huygens. I don't know how to pronounce it.
Huygens.
But, sure. With the double slit experiment, he concluded that light was a wave. But it's still...
No, but that was later. That was 1923. That was later.
To that point. Sorry?
Yeah, because again, the Newton thing, the Newton thing, obviously,
experiment was in 1923.
Young's double slit experiment, the whole wave particle duality was after Einstein had already proposed that light was available in packets, right? Because the whole quantum theory of light in 1905 had proved that
I think that's very false.
What? I'm quite sure that the double slit experiment occurred after. I mean, to be honest, I could be wrong. Maybe you can show me, but I'm pretty sure that.
I'll Google it.
When was the double slit experiment?
Thomas Young in 1801.
Oh, 1801? What was I reading? Was 1925? I was 1923. Yeah. I read the wave particle nature of light.
1927 was Davison and Germer demonstrated that electrons have the same behavior.
Oh, well, I guess that was a little later. But, well, again, a big part of Einstein's quantum theory of light, was basically classifying light into these packets of quanta. Basically saying that, light doesn't travel continuously, but it has a discrete spectrum. And this discrete spectrum he devised using the Planck spectrum. So if you actually see the energy equation for light, it has discrete intervals of Planck's constant times frequency, hf. So E equals hf is like a very famous equation that Einstein came up with in this quantum theory of light. And again, maybe clearly I stand corrected. He wasn't the first one to prove that or to show that it came in packets. But what he did was he defined this definite spectrum that light will always follow. And that was a very important idea to then discover the photoelectric effect, right? The photoelectric effect is basically when light hits a certain metal with what is called a work function, but basically a metal with a certain, with certain properties, let me just say that. If light hits it at a certain energy, at a certain frequency, the metal will emit electrons. So you are able to run those electrons through a wire and then we'll get electricity. So basically the idea of a photovalve or like your solar panels was come from the photoelectric effect, which again comes from the fact that light travels in these discrete quantities, right? So that was a big thing that he did that was one of his first papers. Maybe we want to get into Bohr. Maybe we can go like back and forth with some of their papers to see if they stack up with one another.
So one of the best things, I don't know, this is very subjective obviously, but one of my favorite contributions from Bohr to the physics world is actually the Bohr model of the atom. And so when you're in high school, you're in chemistry class, you'll learn about the Bohr-Rutherford model for the atom. And what you learn is that there's a nucleus which is positively charged and is quite massive, and then you have these lighter negatively charged particles that orbit around the nucleus in certain how do I say this, like, you know, it's the 288 electron,
Like the configuration.
distribution, I guess. Yeah, the configuration. Yeah. And so Bohr's model for the atom is like it follows the same it's along the same lines. I'm pretty sure like the Bohr-Rutherford model is slightly different from just Bohr's model for the atom. And when you learn about Bohr's model, we usually just talk about the hydrogen model, the hydrogen atom. You don't really go into the other atoms. And so what you have is the nucleus and a single electron. And so what did his model say? Well, he said that you have these energy levels around the nucleus that grow in radius, right? So if
that's the difference, by the way, between Bohr and Rutherford. That Rutherford's model does not describe the energy levels, and Bohr's does. So that's your difference.
Yeah, and it's actually a lot more complicated to like describe these energy levels when you have more than one electron. So that's why we just explain it with one electron in the hydrogen atom. So you have these energy levels, and these energy levels are quantized, you know, which is why, you know, we teach this in a quantum mechanics course, because it takes you through like the history of how what we know today has come about. And of course the Bohr model of the atom was very, very groundbreaking. And here's why. And when you realize this, at least for me, when I was learning this in class, I was like, this makes so much sense. There's experimental proof and all that stuff. This is amazing. Okay, now let me explain it. So you have these energy levels. Electrons can emit or absorb packets of light, aka photons. Okay, and obviously, as Ray just explained, photons can have different quantized energies as well. And so to go from one energy level to the other, it's actually, I'm not going to get too mathematical, but you need a certain amount of energy to either climb the energy level ladder, and when you go down an energy level, you have to emit a photon of a certain energy. And so the reason why the energy levels increase in energy the further away you are from the nucleus is because what's quantized in an atom, or for an electron going around an atom, is the angular momentum. And so if you I was gonna say, like, if you draw the wave that goes around, what you have to do is kind of match up the wave, but I guess we're not really talking about wave functions. But what I was gonna say is that the further away you are, the bigger your, like, if you calculate angular momentum, there is a factor of distance away from your point of rotation, and so the more energy you have, the further away, because you're not changing the mass of the electron. So the more energy you have, the further away you have to be from the center. The reason why this is groundbreaking, though, is because people would look at like, they would burn elements and they would look at the spectrum of light that comes from that emission, right? Or if you look at stars, which is the same thing, just hydrogen, other elements emitting photons, you would see like the visual spectrum, of course, and you can also analyze above and below the visual spectrum, but you would see these lines of just like a certain wavelength just missing. And for so long, people were just like, okay, what do these lines mean, first of all? And why is it that when we look at hydrogen, we always see the same lines? When we look at a different metal, a different gas or whatever, we see different lines and different spots and all that stuff, but it's always constant. And what actually explains this is the energy levels. And so when you look at a hydrogen atom, you look at the hydrogen spectrum, you'll see a line at the exact position where if you were to calculate, as Rehan said, you do the energy is equal to Planck's constant times the frequency. You take the frequency at which in the spectrum of light there's a line, there's like a missing photon, let's say. What happens is that photon is the exact energy that it takes for an electron to go, for example, from the first energy level to the second energy level. So when you're asking, where does this light go? Why is there a missing slit in the spectrum? It's because the hydrogen atoms would absorb that light and move up an energy level. Mm-hmm. And then, of course, there are different missing pieces at different spots, because to go from 2 to 3, 3 to 4, you need different amounts of energy, which corresponds to different wavelengths of light. So mm-hmm. Yeah.
And that's Bohr for you. At least that was one of his very large contributions. And one thing I did want to mention, I did search it up, and yeah, so Einstein was actually the very first one to prove that it does come in particles. Newton had thought about it. The wave-particle duality nature of Young's double-slit experiment was actually shown in 1925, but even though the experiment was done in 1801, it was basically just showing that light and electrons could be thought of as waves. It wasn't showing that they could be thought of as particles. Yeah. So that whole particle thing started with the quantum theory of light that Einstein released.
No. So what you were saying was that before Einstein, people thought of light as just a wave, and I was saying that's not true. Some people thought it was particles.
Okay, well, yeah, some people thought, but there was no proof. What I'm saying is there was no actual proof behind the fact that it was a wave, that was a particle. And then Einstein came out and was like, yo, it is. So yeah, so I wasn't entirely wrong. It's just that, yeah, so the double slit experiment had happened before. It's just that the wave particle nature had come in a little bit later. So yeah, so that was, one of his very, very famous theories, and I'm pretty sure I mentioned it. I don't know if I did, but in 1921, it won him the Nobel Prize for the photoelectric effect. Very, very well known. Interestingly enough, everyone knows him for like E equals MC squared. This with special relativity. We're gonna get into that, but that's not what he won the Nobel Prize for. Even though that is what he is most known for, it's actually the photoelectric effect. The simple solar panel, that we all have today. That he came up with.
The photoelectric effect is pretty crazy, though.
It's amazing. It's an amazing way to think about how light distributes energy. And again, very similar to what you just said. That's also how it works, right? You said, well, if an electron wants to, like, if it's moving up an orbital, it's going to be gaining energy. If it's moving down an orbital, it's going to release energy in terms of a photon. So again, if a photon comes into the metal, and it's giving the atom more energy, what's the electron doing? The outermost electron is basically just escaping. So that outermost electron is then what's taken in to be electricity, right?
You can explain the setup of the experiment, because you haven't done that.
With a photoelectric effect? Mm-hmm. I thought I touched on it. Just like, it's just a metal, basically, and there is a wire that runs through it where the electrons from that metal get knocked off into that wire, which then conducts the electricity. So as long as there is light that is traveling at a certain frequency, depending on the metal, and obviously you can do a calculation for the sun and stuff, hence the photovoltaic panels.
I think you're missing like a little bit of detail. Like,
okay, maybe you want to fill it in? Maybe what am I missing?
You have two metal plates that have an electric potential difference between them, right? And basically, you can have like some kind of like a light, for example, that will turn on if there's current in between. Like the two plates are connected together by a wire, and then to tell if electricity is actually being conducted between the plates, you can put like a light or something just to see if there's electrons running. But essentially what you do is you shine a light onto one of the plates, and I think it's like the negatively charged plate, that you shine a light onto it. And then what happens is that depending on the frequency of the light, of course you talked about the work function a little bit, and that work function essentially binds the electrons to the negatively charged plate. And so when you shine a light, what happens is that these photons are like flying through the air towards the electrons that are bound by the work function. And so if your electrons have a certain amount of energy that exceeds the energy of the work function, the photons will be able to knock the electrons away, like off of the plate, and then they will be attracted by the other plate, like the positive plate.
The collector plate is what it's called.
Yeah. And so that's exactly what happens, right? If the electrons are knocked off of the negative plate onto the positive plate, then you have a current. And so what happens is that you shine the light onto the negative plate, and what you do is you increase the wavelength. And so you start at a wavelength that is low enough so that it doesn't conduct electricity. And then what you do is you increase the wavelength until you actually do start seeing electrons being knocked away. And so...
do you mean frequency?
Yes, I do.
You mean frequency, right? Yeah.
Yeah,
you increase the frequency. Yeah. Yeah, because like you start off with low energy, and as you increase it, when that energy equals the work function is when it'll start emitting, but when it exceeds it is when you have electricity. You have a flow of electricity. Yeah. And then that's your whole idea behind your photoelectric effect. And it's beautiful. It's a beautiful theory. And I mean, and that's not it though. That's not it for 1905. Right? Remember, this is the year of miracles for Albert Einstein. His second paper that he released in May of 1905. It was May, and I believe there was also like an update or something in June. There was like some collaboration. And this paper was on something known as Brownian motion. So Brownian motion is actually something that was discovered in 1827 by Robert Brown. And he saw, when he immersed flower pollen, into water, he saw that even when it was completely stationary, like complete at thermal equilibrium in a totally isolated environment, nothing was affecting it, the individual pollens would be vibrating, would be moving in the water. And again, this might be like, well, what's the big deal, right? Like, but again, as a scientist, you might be like, well, why are these things moving? And it turns out that was the very first experimental evidence of an atom, of atoms, basically, showing that there is something smaller than just water. That in the water, there's something in there that's causing these pollen to move. Anyways, many years later, obviously 1905, this is when Albert Einstein releases this paper on Brownian motion. He basically describes... Now remember, Brownian motion is also, I should have mentioned this, is also kind of characterized as random motion. Because there are all kinds of... there are just atoms in this system. What are atoms doing? They're just moving, like individual atoms are just moving in all sorts of directions. There's no uniformity to them. When you say, like, atoms usually are not all going in the same direction. If you find, for example, an equilibrium or some sort of, if you have like a magnetic pull, sure, you can maybe face them in a direction. But on average, or individually speaking, all the atoms are just everywhere, random motion. Einstein comes in and he basically devises an equation for this motion. Brownian motion. And it's surprising to everyone, more so because of what this proves. This is the first ever mathematical proof of an atom. Basically saying that atoms in the water is what is causing these pollens to move. So microscopic movements from the pollen, for example, like there might be a little more concentration of atoms moving in one direction than the other. So the pollen is vibrating. There might be a little in the other direction, and their pollen is vibrating. So basically, it's just because of this random motion that then Einstein described using this theory that he then called Brownian motion, was again explained as the very first proof of an atom. Again, further just breaking science. Just completely breaking.
Yeah, that's crazy. Especially because
this guy.
one, he kind of discovered that. Well, he didn't discover it, but he like analyzed the situation, came to a conclusion.
Mm-hmm.
And then later in his own lifetime, he got to see like all of these advancements in our understanding of the structure of the atom. And then, you know, I don't know the exact timeline, but by the end of his life until today, like has our understanding of like the model of the atom changed that much? Do you know?
I don't think so. Because when we're talking about the classical, just the Bohr-Rutherford model, like we're still taught that in school, and that is what we learned for a long time, right? Like the quantum model is taught, you know, in years of university. So I think it's still applicable just for like energy levels and stuff. Remember, like, you know, quantum model is just like, it just overcomplicates a lot of things, but just to understand the discrete nature of energy levels and everything, you know, just drawing circles around a nucleus works. So yeah.
And you actually, I think you talked about like the alpha particle experiment in a previous episode.
Yeah.
What year was that in?
The Rutherford gold foil experiment? I don't know off the top of my head. I can definitely search it up.
Okay.
But yeah,
I think it was before.
Yeah, you want to maybe give a quick recap for the gold foil experiment? This was Rutherford's experiment that he did.
Yeah, and actually Bohr worked with Rutherford to work on his model and his theory of the atom. But this actually, like the way that Bohr came up with his model is that Rutherford performed this experiment where he shoots alpha particles, positively charged particles, to like through this gold foil. Most of the particles would just go through the foil, but some of them would actually be deflected at a certain angle and even reflected backwards. And so his conclusion was that there has to be some like very concentrated area or volume, I guess, of positively charged subatomic particles. Yeah. And then that's when people started thinking about like the less massive negatively charged particles that would be orbiting around this nucleus. But just the fact that most of the positively charged particles went through implied that, you know, the nucleus is very small. Because if the nucleus, like for example the plum pudding what's it called, the plum pudding
model
of the,
just the plum pudding model of the atom, right?
Yeah, we're
talking about
so if that was true, then you would see like tons of deviations for the alpha particles, because they would always be in this like electromagnetic field when going through the gold foil. But the fact that most of them just went straight through meant that most of the stuff is just nothing, right? Which is actually true. The nucleus like takes up less than like 0.00 I don't know percent of the volume of an atom.
Also, this was in 1911. Just wanted to mention that. So this was quite a lot after, about 6 years after Einstein's whole idea of atoms. And again, this is also where a lot of them, you know, where you can see a lot of similarities. And again, the reasoning behind why we chose Bohr and Einstein today, you know, like they come in a lot of equations, they come in a lot of things together. And obviously, I mean, we're going to continue talking about them, and it does get a lot more exciting. So yeah, so maybe want to continue with the cool Bohr experiment or something. That
yeah. So the thing about Bohr is that he was very involved with the future generations of physicists. And now, how dedicated was he? Okay, well,
Let's hear
so
it.
in 1916, he was offered a professorship at Copenhagen University. But at the time, the physics department at the university was very small. It was just like this tiny section of the university. And he was like, you know what? I will accept the professorship and all that stuff, but I want to build an institute for theoretical physics at this university. And, his demands went through, and the university built the Niels Bohr Institute of Physics. I think the name changed over time. Now it's just called the Niels Bohr Institute. I think before it was called like Institute of Theoretical Physics, something like that. And what he did was he hosted a bunch of, up and coming physics students from, I think, mostly around Europe and a little bit, a few students came from America, but it was really like the top students that came to this university. And this is a crazy move for Bohr, because he said, you know what, people can be smart, right? You can think of smart ideas, but the way you move physics forward is by connecting smart people together so that they can connect their ideas and move forward. Like where would your insert favorite physicist here, right, be without communication with the outside world, peer reviews of their papers and just chats about their ideas. Mm-hmm. Like, this is what I think about this, and then someone else pulls out and he's like, no, this is what it is, here's why, here's my experiment, all this stuff. So what Bohr did for the physics world is that he brought together the smartest physicists, the smartest students from all around the world to come study in one location and to just bounce ideas off of each other. And so this is not like an experiment or anything, but this is what Bohr did.
It's pretty cool.
And I think it opened in 1921 in March. So 100 years ago, a little bit more than 100 years ago now. But the thing with this institute is that it hosted a lot of students. For example, Werner Heisenberg, who actually went to this institute.
Classic.
And I'd love to talk about Heisenberg as well. But the thing about this institute is that a lot of the students, or I guess a few of the students, were working on quantum mechanics at the time, or I guess at the time it was called matrix mechanics. And then you had other professors in other locations that were working on wave mechanics. It turns out that matrix mechanics and wave mechanics are just two different ways of explaining the same thing, and they're actually compatible with each other, meaning that, like, if you add, like, if you do multiplication but you do it like cross and add, or there's different ways to multiply, but it all does the same thing. It's the same idea here. The students at the Bohr Institute, they were dealing with the matrix mechanics side, the more like the quantized explanation for what we see at a small scale. Nowadays it's just called quantum mechanics, but back in the day it was separated because there were different philosophies behind different ideas. Schrödinger, we should talk about Schrödinger actually.
Schrödinger is also in this time period.
In a future episode.
All these guys are in this time period is insane.
Yeah.
Like, this time period, the 20th century is such a revolutionary time period for science. It's just crazy. It's just crazy. Yeah, sorry, continue.
And by the way, I should have mentioned this earlier, but if you are interested with all that we're talking about right now, I read a book called Quantum, I think like The Great Debate About the Nature of Reality by Manjeet Kumar. Crazy book. Goes through the entire history from beginning all the way to like the end of this like quantum revolution. Like starting with like, how did like this idea of quantized energy and all, like, why are things quantized at all? Mm-hmm. You start with the very beginning in the 1800s with Max Planck having discovered black body radiation, and then so on and so on. Einstein comes into the picture, Bohr, Bell, which we can talk
Bell's
about
theorem.
also.
Oh yeah, for sure we can.
All these things, they come together, and somehow we formulate this explanation, and this is where we are now.
Yeah.
Anyways,
and the interesting thing about Einstein is, especially again, even though he did start the paper on the quantum nature of light, he didn't actually, and we're going to get into this, he wasn't actually a big fan of quantum mechanics. He was actually a very heavy believer in the hidden variables theory. And we are going to get into that. Now it's still too early because we're still 1905. We are going to get into his whole hidden variables and, his whole phase where he just completely rejected quantum mechanics. And he wrote the very famous phrase, "He does not play dice." Basically talking about the fact that the universe can't be probabilistic. I think
we run out of time near the end.
Yeah, but I think we can close maybe touch up on some of this stuff because it's really cool, especially in his life. So, anyways, continuing on to 1905, and a lot of things in 1905. Don't worry, I'm gonna hurry it up though. In 1905, the last paper that he published, and I think you know where this is going because there's only one more remaining. The special theory of relativity. So this happened in June of 1905. However, the very famous equation, E equals mc squared, wasn't released until September of that same year. And he basically, I believe, updated his paper including that equation, even though that exact equation wasn't actually written on his paper. It was actually a Pythagorean identity that can be reduced to E equals mc squared that we very well know now. But again, the big thing...
I don't know why, but that reminded me of an artist dropping a single. He's like, oh yeah, by the way, here's a track here. Here's E equals mc squared. Everyone's like,
just just an extra guy, just a little bit of an extra one. Yeah. So again, the big thing with this is not really the equation or the math behind it, because everyone's like, oh, E equals mc. No, the idea is what that equation means, and that equation means that, or basically it represents a relationship between energy and mass. No one had ever really thought of before. That mass is nothing but energy and can be converted into energy. And energy, again, can be represented as some level of mass. So understanding that energy and mass are interchangeable, basically they're correlated to one another, was his big special relativity discovery. And we have a whole episode on it. But it's a really cool, it's obviously one of his most known theories. And yeah, so that completes his annus mirabilis. I don't know if I'm pronouncing that right. Annus? I think it's annus, right? I'm not sure. Continuing though, in 1910, we have a very famous question answered also by Albert Einstein. Why is the sky blue? Now you must be wondering, well, wait, I learned in high school that's called Rayleigh scattering. For any one of those guys that remembers Rayleigh scattering. However, Rayleigh scattering basically says longer wavelengths get scattered at different ranges than shorter wavelengths. What Einstein proved in this paper in 1910 was the atomic nature of the scattering, something that hadn't been done. Because what Rayleigh scattering simply represents is the angle at which the light hits the air, basically refracts, hits all the, hits the general air, not the individual molecules. Einstein came up with a paper and an explanation for what is happening in the atomic level. And he basically spoke about how the scattering occurs on the molecular level, something that hadn't been done before. And again, answering the age-old question, why is the sky blue, with a very complicated answer. But basically just like an advanced Rayleigh scattering, just continuing his theory, right? So yeah, so that's a little bit of him. You want to maybe talk about Bohr before we get into the big general theory?
For sure. Yeah, so kind of, if I had to pick one last thing to say about Bohr, it would be definitely the conversations that he's had with Albert Einstein himself,
Ooh,
right?
yeah,
The
for
biggest
sure.
crossover in the history of all of physics. And these conversations happened at the Slove conferences, which was this like a summit of the best physicists around the world. This was very subjective, of course. Slove himself would just compile this list, and he did leave out some people, and it did get kind of political, but we're not going to get into that. But Bohr and Einstein met up a couple times, actually, and they talked about their views on quantum mechanics, and Einstein was actually against Bohr's ideas. Bohr and his new students at his institute came up with the ideas of like the uncertainty principle, and they're just some things that you don't know. Like the universe is probabilistic. The most you can know about something is the probability distribution. And Einstein was completely against that. He was saying that the universe is deterministic. God does not play dice, the famous quote. And for example, you also said hidden variables, right?
Hidden
What are
variable
hidden
theory.
variables?
He was a big advocator for that one. Yeah, for sure.
Yeah. So a hidden variable is basically like it's like information that we don't have access to, but is still there, right? And this hidden variable could be due to like lack of equipment. We just don't know how to like extract this information, or it's just like there's no way to actually get this information, but it's out there. It's out there somewhere. Anyways, the point of like hidden variables is it's basically admitting that we are not smart enough to tackle this issue here.
Mm-hmm.
One of the problems was like the entangled particle, where I mean, like briefly, if you have like a spin zero particle and then it splits off into two directions, and then you have like one of them is spin up, one of them is spin down, so that it cancels out. The thing is that if one person detects one of the particles, they know exactly what the other particle is, even if the particle is light years away. And this made no sense to Einstein because that's kind of like relaying information across the universe faster than the speed of light, which is very against the rules. And so this is why he believed in hidden variables. He said, this is not possible. There has to be like something hidden that we don't know yet, but there's a bigger theory out there that will encompass what we know about quantum mechanics, what we know about general relativity, and it'll all make sense when we do figure out this larger theory. And Bohr was like, I don't think so. I think like this is just what the universe is, right? The uncertainty principle Einstein really didn't like because it was saying that you can't know position and momentum, but intuitively you think, well, I can just find the momentum, find the position, and how can I not know both? There are really subtle arguments that you can make to show that this is not possible, which we have talked about in inventions. What was the episode called? Historic inventions, something, or experiments.
It was a recent episode. It was a play on the history of physics episodes, but it wasn't a history of physics episode where we were talking about famous experiments.
It was called Experiments That Changed History.
Changed history.
And,
cool.
Yeah.
Yeah, that's a really cool episode. Yeah, for sure. Yeah, and so because you already mentioned, I guess I can go a little ahead because I just want to talk about like a few more really notorious things that Einstein did. But because you already spoke about entanglement, I guess I can start with that. So in 1935, Einstein, Podolsky, and Rosen, Nathan Rosen, and Boris Podolsky wrote the paper on the Einstein-Podolsky-Rosen paradox, now known as the EPR paradox, which basically, as you just said, is asking the question, well, or not asking the question, but the whole paradox is basically, how can we know this information? How can this information be relayed across the universe, like seemingly faster than the speed of light, right? Now, the whole idea behind this, however, even though the EPR paradox is a very famous paradox, it was solved and it was proven to, well, not work, because the whole idea behind quantum entanglement is that, as Barker just said, again, if you have a spin zero particle, you send one with spin half, one with spin negative half, right? The moment you don't know which one is which. Let's say you send them on opposite sides of the universe, you measure one, you see that one is positive half, you already know instantaneously that the other one is negative half. You know that for a fact, for a 100% fact, because that is simply the nature of these particles. They're entangled. And however, again, the whole Einstein version was that, well, information is being traveled faster than the speed of light. No. The Copenhagen interpretation, or the quantum mechanical interpretation, is that, well, the moment these particles left the spin zero, like the spin zero broke up into these two, there's a thing called a wave function that basically represents the position and the states of these particles. So the wave function of both of these particles are identical throughout history until we make an observation. And the moment we make an observation, quantum mechanically speaking, this wave function, again, that simply represents that it can either be plus half or minus half, it collapses into one of them. So, via quantum theory, we do not break any of the paradoxes, any of the known laws that we come to have understood today. Because all of our quantum theory is based off of the fact that the universe is in fact probabilistic, or the Copenhagen interpretation of quantum mechanics. At least that's today. So when these guys tried to release it in 1835, it was obviously a monumental thing, and I believe Bohr was a big part in, well, proving it wrong, in basically saying that, well, no, it's not a paradox because you can explain it using quantum mechanics. And I believe all the way up until Einstein's death, he did not believe, right? He did not believe in quantum mechanics whatsoever. He was very fixated on the fact that we just don't know enough about the universe and hidden variable theory. Right? Yeah. That's a pretty sad reality. But well, we have quantum theory today. It makes sense today. Who knows? In like 200,000 years, maybe we have a brand new theory.
Yeah, I mean, Einstein, like, he has the Einstein's biggest blunder, or whatever it's called.
Yeah, I was gonna get into that with general relativity next. Yeah.
Yeah. Well, essentially, it goes to show that, even when Einstein is wrong, he's right. So maybe,
You never know, maybe, man. Maybe this guy knows something
in 100
we don't.
years, in 100 years, something will come out and it'll be like, oh, yeah, no, Einstein was completely right. But now we know, and now we're smarter. And, they'll look back to the Math and Physics podcast and be like, wow, we really couldn't just like do this one experiment and figure out like how obvious it is.
Yeah, so that's that's the power of Einstein, right? Like, and again, when you just said the biggest blunder, let's get into that maybe as the closing. I did want to get into Bose-Einstein condensates, but I guess like that's just like an extra. He's done a lot of things in his life, man. Like, I don't think we can get into all of it. Mm-hmm. He's done a lot of cool things. But anyway, let's just end on the highest note, the general theory of relativity. So in 1915, Albert Einstein writes this paper, and interestingly enough, he had started to think about it. Well, after special relativity itself, he started to think about, well, what if we start changing these frames to non-inertial frames? But in 1907 was the first, I believe, the first instance of him actually thinking about the relationship between acceleration and gravity, and thinking about, well, is gravity, what we see on Earth, the same thing as accelerating in a spaceship? And this is the very famous this is one of Einstein's postulates, where you flying in a spaceship is the same as you on Earth. And you're like, well, how is that possible? And that is basically, a consequence of what he proves here. So The general theory of relativity is basically a way to say, screw you to Newton, and say that, well, gravity isn't anything. It's not really a force or anything. It is simply a consequence of what we call the space-time manifold. What we call space-time, or space, well, what we call space, when our Earth is sitting on some block of space, gravity is simply the consequence of that block having mass. Anything with some amount of mass will depress the space-time the space-time curvature, like it's called. And he came up with this idea that, well, gravity isn't really an attractive anything. It's not a force whatsoever, but it's simply because, well, space is curved. So everywhere you're going, the reason you look like you're moving in an orbit is not because you're actually moving in an orbit. You're just going straight. But it's space that is actually curved around the body to make it look like a circle. But what you're actually doing is simply going straight. But it's space that's curved. So he explained what we see in reality, in nature, in a radically different way, using the general theory of relativity. And I believe he published it actually in 1916, and then in 1919, a bunch of astronomers, as you were mentioning before in the podcast, they were witnessing an eclipse where they saw the first proof of gravitational lensing, i.e., gravity bending light. Again, if Newton was right and gravity is a force, gravity should not affect light, right? Because light is massless. However, Einstein proved that, again, gravity has nothing to do with mass, or at least not the mass of the object. It's simply with the curvature of space-time. So because space-time is curved around the sun, we can see objects that we generally would never be able to see because of the fact that the light is curving. And again, this was simply a consequence of his general theory. And that's Einstein for you, revolutionized science in 20 years. Less.
A
Crazy.
Great way to think about this, which is, it always blows people's minds when they think about this. But imagine this, okay? Imagine you have a rock and you're in the middle of deep space. There's no gravitational field anywhere around. And let's pretend like you're a ghost, you don't have a mass. Okay. So you're sitting in the middle of nowhere and you throw the rock. And the rock draws a path behind it, right? You're just going to see a straight path. It's going to float in a single direction at a constant speed. That's all you get, okay? Now, let's come back to Earth. You have that same rock, and you throw that rock in the same direction. What happens to that path? That path gets curved down towards the Earth. But that's not that has nothing to do with the rock. It has to do with where the rock is in space. It just so happens that the space is curving its path. And the thing about space-time and why it's so hard to think about curved space-time is because you need to consider the time dimension as well. And that's why I say imagine the path being drawn out. So in deep space, there's no curvature happening, right? You just throw the rock, and throughout space-time, all four dimensions, the path is completely straight, and it will continue to be straight. But on Earth, or let's say you're in Earth's orbit, and you throw a rock in front of you, that path, depending on the velocity of the rock, of course, but let's pretend it's going at
if you're in orbit, it will remain in orbit, right? Because it's already traveling at 7,000 plus kilometers a second.
Yeah, but let's say for example, you throw it behind you, and then it slows. But the point
okay,
is,
well, I understand.
the point is that if you throw that rock is not just going to go in one direction and just keep going, because the space-time that it's in is literally curved. And so that's going to, as time plays out, the path of that rock will be curved, and you can literally see it with your own eyes. So,
And a very famous thought about bent space is, putting a ball on a carpet. But that's a terrible way to think about it, because what you think about is that the ball, that anything you throw outside will eventually come in. But that's just not how space works, right? That's just not how it works. There is a certain level after which you cross, you will go in, right? That is simply a fact with anything. If you're really close to the planet and your orbit, has some certain properties of hitting the planet on your next cycle, well, you will hit the planet, But if your orbit is large enough, again, that carpet definition doesn't make you understand it, because then again, it all eventually comes to the center. But that's not actually what space is. It's more like just a little blip, and then okay. I guess I can't really. I just thought about it. I can't really explain it too well.
Let's just.
Especially to the audio listeners, this might be terrible. There's not really a way to do it. But anyways, there are visuals of how to think about curved space-time. So you might want to search up. And again, this is all a consequence of the general theory of relativity. Thinking about space as a thing that can curve, a thing that can move. The famous expression, space tells is it the other way around? Wait. Space tells matter how to move. Matter tells space-time how to curve. That's the famous quote, right? Matter? Yeah. Or is it the other way around? Yeah, matter tells space-time.
It's the other way around. No, you first you have to say matter tells space-time how to curve, and then curved space-time tells matter how to move.
Matter how to move, right? Yeah. Okay. Sorry, I messed up the order. But yeah. So the idea is basically that matter is simply moving along a path that is set by space-time, right? If space-time is bent, however you throw it, it's gonna follow that path, And that's the beauty, and that's the beauty of this theory, and that's the beauty of of general relativity.
That's Einstein and Bohr for you. We hope you enjoyed this episode. Let us know who you want us to talk about on the next episode of the history of physics. We're pretty much open to doing anybody.
We're doing Turing, for sure. I really want to do Turing, because I started reading up on him, and he has some very interesting computational problems. He's he's the godfather of computer science. He's the guy that started it all. So it might be a really interesting conversation with Turing. Maybe we can think of another.
I kind of want to do Nikola Tesla, to be honest. So we might do Tesla and Turing.
Tesla and Turing? Why not? I mean, again, I think this episode was very apt. Very, very apt, because these guys go together hand in hand. Quantum theory, quantum rejector, and then one is again following Planck's footsteps, one again deriving a lot of his theories from Planck. So they're very similar time frames, timelines, when they were born and stuff, and they have very similar ideas about the universe. So it was a very nice episode that we had today with both of these gentlemen. But maybe Tesla Turing next time. Who knows? Let's see.
So make sure to catch us live, maybe, on Instagram at math.physics.podcast. And make sure to give this episode a rating. Give the podcast a follow. Ooh. Who knows what'll happen? Maybe we'll give away $1 million. You never know.
That would be the day.
So yeah, this has been episode number 61 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.